We are talking about covalent bonding today. So covalent bonds, very similar to ionic bonds, but the big difference is going to be instead of transferring electrons, we are sharing electrons. So both elements are going to still have the electron that they originally had, plus they're going to be sharing this other one, and it'll be a part of their atom now. This is going to happen between mainly nonmetals, so it's going to be anything that's in green. So all of these in this little corner, hydrogen's included, and with the exception of beryllium and boron. So beryllium's a metal that's going to be included, boron's a metalloid, and they are both going to do covalent bonding. Beryllium is going to basically determine what bond it forms based on the electronegativity, which is the attraction between atoms. So between electrons. Whoops. Boron, it's going to form 3 covalent bonds with their 3 valence electrons with other nonmetal atoms. The whole purpose of sharing and the whole purpose of bonding is to gain stability. And you do that by meeting the octet rule, which is basically... it's not even 8 electrons. It's just a full outer shell, because there are some exceptions. Full outer shell. The exceptions are hydrogen's only going to have 2, boron's going to have 6, sulfur will have 10, and phosphorus will have 12. When they're stable, we consider it having a noble gas configuration, which basically means it's just non-reactive. It's happy where it's at. It doesn't feel the need to bond or be reactive because its shell is completely full. These are going to form molecules, and because of this bonding, the potential energy is going to be lower as well. They share electrons when they aren't able to lose or gain one. So basically, remember, ionic bonding happens with metals and nonmetals. If there's no metal around, it's going to just take whatever it can, and it's usually going to be a nonmetal. Electronegativity, there are different covalent bonds depending on what it is. So if it has an electronegativity between 0 and 0.4, it's going to be a non-polar covalent bond. 0.4, we say 1.7, but as long as it is less than 2, I don't know what happened. It's going to be a polar covalent bond, and then 2 to 4 is going to be ionic. This is the electronegativity of our elements on the periodic table. Hopefully you remember the trend, but as you go down the table, it is decreasing. As you're going across the table, it is increasing. Increasing. So cesium is going to be the element that has the least amount of electronegativity with 0.7 because it's furthest down and bottom left. And then fluorine is going to have the highest because it's the highest top right. So helium, neon, argon, krypton, xenon, the noble gases, they are not going to be reactive and have no electronegativity because they're happy. They don't need anybody else's electrons. These are our diatomic molecules. Basically, they, naturally on Earth, they are found in their pair, which just means that they are bonded with their with a second of itself. And those are hydrogen, nitrogen, oxygen, fluorine, chlorine, iodine, and bromine. These are examples of the Lewis structure. We're going to talk about this more in a different PowerPoint, but I just wanted to introduce it. Lewis structure, remember, it shows the outer shell. And to show that a covalent bond has happened, instead of putting a dot here and a dot here, you're just going to connect them. So we'll pretend that that dot has gone away, and these two are just connected by this bar. Same thing for oxygen, which is showing more than 2 atoms. And then sugar, this one's got a lot going on, so this one is a little bit more crazy because of how many bonds it has. In order to determine the number of bonds, there are some rules. So you're going to add up all the valence electrons in the compound, so what you start with. Or let's call this what you have. Then you're going to add up all the valence electrons of what your final is. Basically, what you want / what's the goal, what you want to end up with. Most atoms are going to have 8 in their outer shell, but there are the exception of hydrogen and boron. And then what you're going to do is you're going to take your final, so your goal or your want, you're going to subtract that by what you are, what you have / start with, and then you're going to divide this all by 2. So we'll do some examples. I really don't want to use this one, so we're going to go into these. So I like to make a little table, whatever works for you. There really is no preference. So I'm going to start with what I have. And then this is what I want. And we're talking about valence electrons and all of this. Let's thicken up the marker a little bit. So let's look at this first example. CF4. So I'm going to start with carbon. Carbon has 4 valence electrons. Carbon wants 8 valence electrons. Fluorine has 7 valence electrons, wants 8 valence electrons. You have 4 fluorine molecules, so I'm just going to repeat this until I have 4. Okay, then we're going to add this all up. 7 times 4 is 28, plus 4 is going to give me 32 valence electrons. I have 32 valence electrons in CF4. I want to have 40 valence electrons in CF4. So I'm going to take my 40, what I want. I'm going to subtract what I have from it. So 32. And then I'm going to divide this all by 2. So 40 minus 32 is 8. I'm going to divide that by 2. And I'm going to have 4 bonds in this first example. Okay? Let's try the next example. Hopefully that made a little bit of sense. But if it doesn't, we got another one. We're going to go with O2. I have 6 electrons in oxygen. I want 8 electrons. We're going to do it twice because there's 2 oxygen atoms. 6 plus 6 is 12. 8 plus 8 is 16. I take my want. I'm going to subtract my have from it. I'm going to divide it all by 2. 16 minus 12 is 4. Divided by 2 is going to be 2 bonds. Okay? Let's do the other examples. So CH4. I have, my want. I have 4 valence electrons in my carbon atom. I want 8. I have 4 hydrogens. Instead of writing it 4 times, I'm just going to multiply everything by 4. So I have 1 valence electron times 4 is going to give me 4 valence electrons. I want 2 valence electrons times 4 is going to give me 8 valence electrons. So we're going to add this up. 4 plus 4 is going to be 8. 8 plus 8 is going to be 16. 16 minus 8 All of that is going to be divided by 2. 16 minus 8 is going to be 8 divided by 2 equals 4 bonds. Okay? Very similar to that first one we did. And then this last example, bromine, Br2, is very similar where I'm just going to multiply. Bromine has 7 valence electrons times 2 is going to give me 14 valence electrons. I want 8 in my outer shell. Multiply that by 2 because I have two atoms of it. This is going to give me 16 valence electrons. 16 minus 14 equals 2 divided by 2 equals 1 bond. Hopefully this helps. This is where we're going to stop for this video, and then tomorrow we will do the second lesson.